Recording in progress.
With the partition functions for individual degrees of freedom. And in particular, we discussed that we can do this if our energy is to a good approximation. This is an approximation additive in the different modes of the energy, or also we also call that the different degrees of freedom. So the vibrational degrees of freedom, the translational degrees of freedom, the rotational degrees of freedom. Now, we discussed the partition function for the translational degrees of freedom already, and we started then last week with the partition function for the rotations in your system. And in particular, we considered this example here of the diatomic harmonically vibrating rigid rotor, and we wrote the partition function as a product of vibrational, rotational, and translational contributions. And we had identified each of those as these three factors here, right? And this one in the middle here, I'm highlighting, is the factor for the rotational degrees of freedom, right? So we discussed their individual contributions, and then I told you about the translational partition function and how we understand it from the quantum mechanics of the particle in the box, right? So we did not solve the corresponding Schrödinger equation ourselves. I hope you did that already in the past, or that you can still do this yourself. This is a well-known textbook example, nothing special about this, and you should find as the solutions for the eigenvalues this expression here. So the distance between the levels grows quadratically with the corresponding quantum number indicating each level. Given this, we inserted the solution in our partition function, and we found out that this partition function, the sum over states, again in German it's called a Zustandssumme, so sum over states, this can be approximated by this integral here, which is basically a Gaussian integral. And for that, we have an analytical expression, namely square root of pi over 4 times the width of your Gaussian, right? The sigma, the length scale of your Gaussian. Once we insert that, we find the expression for the partition function just in one direction, x, right? If we do this for every spatial dimension, also y and z, we then end up with the volume times this bracket here with the beta, the temperature raised to the 3/2. So this was the expression which you had seen already when I gave you, when I introduced the partition function and wanted to exemplify this. And now we did start to discuss the rotational partition function. And for this, we discussed in particular the rotational Schrödinger equation for the rigid rotors. And we had this, this rigid rotor assumption here, basically, where now the solution to the Schrödinger equation is given by this expression. And we like to bundle this fraction into the rotational constant, B, which is commonly also measured in experiments. Now, this is a Schrödinger equation which results from a system which basically consists of two atoms with mass, and one does not have to be the same as the other, and a certain distance r. And it turns out that the Schrödinger equation for this system has a Hamiltonian which is only kinetic energy, so it's only for the rotation of the system. And you have again here the moment of inertia, I, in the denominator, and then kinetic energy, so second order derivative with respect to alpha, and alpha are the angular dimensions in spherical coordinates. The rigidity implies that R is fixed. Okay, it's rigid. So that's the rigidity. This is you can think of this as being crude, right? You would expect that this is not fine, right? R is vibrating, and this is true, but the impact of the vibration, that's what we'll be studying in the vibrational or accounting for in the vibrational partition function, not in the rotational partition function. So basically, that's part of our assumption that these degrees of freedoms can be separated, and we consider them separately. And so we only have to worry about your rotor rotating inside the plane and outside the plane, right? So now this arrow is, so if this is your rotor, right, you have the molecular axis, I can rotate like this, and I can rotate like that, and the third rotation around the axis leaves my system invariant. So it's only 2e. It's a linear system. Okay. I also now introduce what is known as the reduced mass, and that is mu equals m1 times m2 divided by m1 plus m2. So it's something like an effective normalized mass And this is what enters in your moment of inertia as mu times r squared. Right? So the longer the bond distance, right, the more moment of inertia you get, right? So quadratically more, right? The heavier the atoms, linearly more moment of inertia is gained. Now, this is in your this is the I, which then enters your rotational constant B inversely, right? And the rotational constant B enters your level, right? With every level, you grow, right? So the higher levels then, or your energy of the rotational constant is then inversely related to the moment of inertia. Now, there's one more symbol people like to introduce, and this is maybe when you see it the first time, you might think there's a lot of uncommon Norman conventions, but this is quite important for this partition function, and also in the literature you will find this symbol being used a lot, and this is so yet another notation. This is the characteristic rotational temperature tau. We denote it with a little r for rotation, and tau is defined as this fraction here of Planck's constant squared over 8 pi squared moment of inertia kb. And if I use my rotational constant, I can also think of it as hcb divided by kb. All right, so that's the same. Now, this definition allows me to rewrite my eigenvalue, the rotational eigenvalue, epsilon j, as j times j plus 1 times kb tau. Okay. So this is sort of the backdrop, right, of how we tackle this. So basically, this is all. If you studied this already in your quantum mechanics, if you solve that Schrödinger equation, all of these symbols should be known to you. But now we do what's new, which is that we go and we insert this in our partition function, right? So in similar vein, or complete analogy to what we did before with the translational partition function. So let's go insert in Q, right? And that is the sum over our Boltzmann weights. Right? So we now, so this is the general formula. And now specifically for the rotation, we have to sum, and we use the quantum number J, right? These are our rotational quantum numbers. And we now use the fact that we have degeneracy. So there is the prefactor G corresponds to the degeneracy of level J. And we know this Gj is known to be 2 times J plus 1. Right? So depending on your level, right, it grows linear degeneracy. And this is since you have a quantum number Mj, it can go from minus J to 0 to plus J, right? And the energy is degenerate for all these solutions. And so you have J quantum states Mj for the negative and for the positive and for 0. So 2J plus 1. Okay, this is our degeneracy. Since you have all these states and they are degenerate, they are the same, their Boltzmann factor is the same. So I don't have to sum over them individually. They are the same. It's just a multiplicative factor, right? And then I have the energy in my exponential, and this is J over J plus 1. And now if I insert this expression up here, I want to multiply with beta, which is 1 over kBt. Now the kb cancels with the kb in my energy already. And so I have tau r and t left. Okay. So you see in this argument, I basically have two parts. This J times J plus 1 in brackets, and then I have the ratio of my tau r, this characteristic temperature, over the actual temperature. Okay. Now, such a sum, unfortunately, there is no exact closed expression for such a sum for this series. Right? But we can approximate it again. And in particular, if the moment of inertia is not too small, right? That means the atoms are not too light and the bond distance is not too small. Heavy atoms and long bonds, right? We may use what is known as the virtual continuum approximation. And that approximation consists of integrating from 0 to infinity dj times 2j plus 1 e to the minus j times j plus 1 tau r over t. Now, this is this approximation, right? And we'd like to understand what we are integrating here, right? So we're integrating over our index, and here you have your degeneracy, or g here, right? But it turns out that this whole thing corresponds to d, the variation in j times j plus 1, right? So this corresponds to this, since, and let me quickly show you this, if you consider the derivative of j plus 1 with respect to dj, then you have dj of j squared plus j, and that's 2j plus 1, okay? And now if I multiply this with dj on both sides, I have dj j plus 1 from here, and dj times 2j plus 1 from here, okay? So if you do this derivative, you can see that. And now let's simply define this to correspond to x. And we also define a to correspond to tau r over t, okay? And then you see that your approximation becomes dx from 0 to infinity e to the minus ax. Okay. Now, again, similarly to the case of the translational partition function, there is a solution to this integral. So this integral is simply 1 over a. So this is extremely convenient, right? And again, this is an approximation for heavy atoms in large interatomic distances. But if we have that, we can then see, right, we know the definition of our A. So in other words, our Q rot is approximately T over tau R. And again, if we insert the definition of tau R, then we have here 8 pi square moment of inertia divided by h square beta. So this is our rotational partition function, which we have obtained this way. And if I can quickly go back, this is what last week we used here and what I highlighted in the beginning of today's lecture, right? Are there any questions so far? Oh, I see there is in the chat a question. Okay, there was the question, what is the difference between the characteristic temperature and the actual temperature? So we, what we really wanted here is the characteristic temperature to be forming this ratio here. And so it was basically defined to include everything, everything but, so that we could have this ratio, right? Now, you do have no temperature in this definition, right? But it contains your moment of inertia. So it's a measure, if you wish, of the energy. And this is, or the kinetic energy. And this is related then to temperature. So remember, in the Boltzmann factor, we have e to the minus and then energy over temperature, right? So the whole thing, because of KB, the whole thing becomes has no unit, right, in your exponent, and we can interpret this energy contribution as a temperature. So in some sense, right, when speaking hand-wavingly, we also like to interchangeably use temperature like kinetic energy. The higher the temperature, the kinetic energy, and conversely. Now, the rigid rotor is purely kinetic energy. So it makes a lot of sense to think of that energy in terms of a temperature. And then we want to compare that system's temperature to that characteristic temperature. We want to compare it to the actual temperature in your system. And the Boltzmann formalism tells us how. Okay, I should note, right, this is the rigid rotor thing, but of course, scientists then always ask this question, okay, we made this assumption, right? We arrived at this beautiful result. And now the first thing we like to do is to break the assumption and ask, what if the assumption doesn't hold, right? And this is also known as centrifugal stretching, right? this exists, and this will impact your eigenvalues in the Schrödinger equation. So you have to solve a different Schrödinger equation, and the eigenvalues then look as follows. So you have j times j plus 1, kb tau r, and now you have to subtract, right? So it's a lowering of the energy. You have to subtract a term called dj. So this is level B dependent. It's the centrifugal constant, j squared times j plus 1 squared. Right? Now, if you insert that in the approximation, we can see that the Q rod changes by less than 0.1% for all temperatures being less than 500 Kelvin. Okay, so this means that this rigid rotor expression for our partition function, right, this boxed equation here, is great if your interatomic distance is short, if your atoms are heavy, and if your temperature is below 500 Kelvin. Right? There's the question, what happens if the temperature is equals to tau, right? So this is simply your energy here, right? The Boltzmann factor here will this will be set to 1, and this means there's the number of states is you still have your quantum numbers here, right? This is independent of your temperature, right? So the temperature basically just impacts your partition function through this ratio, and this can happen that your temperature the j times j plus 1 just gets multiplied by 1, right? So there are these assumptions, right, in the continuum approximation, and we can look a little bit under which conditions, right, this will fail, right? So the limitation of continuum approximation depends also, so not only the centrifugal stretching, also this continuum approximation, it depends also on the temperature. Right? So in particular, if your levels are getting scaled, then you will have some impact. And in particular, if T over tau R is larger equals 100, then the error is negligible. Right. So the spacing, is it here? The spacing is tau r over t, right? So if t over tau r is larger than 100, means tau r over t is a small number. The spacing is very close by. The rotational levels are close by, right? So close spacing, right? So if you wish, this is the exponent. So yeah, j times j plus 1 over t, then they are close by, right? If t over tau r larger, on the order of 10, then there is roughly a 0.5% error. And then if t over tau r is on the order of 1, then you have on the order of 15% error. Yeah. So these are sort of empirical findings, what you can roughly expect, right? So typically, for diatomics without hydrogen, right? So not too light, T over tau R is larger equals 100 for all temperatures at which there is the gaseous aggregation state. Okay. So for diatomics with hydrogen, T over tau R is on the order of 10 at the boiling temperature. A boiling point. Now let's give some examples. So here we have the diatomic. Here we have tau R over T. Here we have the Q rod. Okay. And the whole thing at T equals 300 Kelvin, right? So that's room temperature. So for H2, that would be 88, and you get a 1.7 Q rod. For HCl, that is 9.4, and you get 32. Contribution of 32. HI, so hydrogen iodide, 7.5, 40. N2, 2.9, 50. CO, 2.8, 110. Iodine, 0.05, 4, 2,800. CO2, strictly speaking, not a diatomic, right? But still linear. 0.56, 270. And now something non-linear, 15 and 1.7. So this is just this you couldn't do with our formula, but we can still get this number and compare it. And what you see now clearly, right, the longest bond distance, the heaviest diatomic, huge contribution to the rotational partition function. You go to a diatomic from the second row, and you have roughly 10 times smaller contribution. You go to a diatomic with hydrogen, and you have again an order of magnitude reduction. So this rotational contribution really can vary by orders of magnitude depending on the composition of your diatomics. Are there any questions on what we have discussed? We are not yet done with the rotational partition function. We'll continue tomorrow. Again, I will send the link via Quercus for tomorrow. I'd like to thank for your attention, and I hope to see you tomorrow then. Bye-bye.